Hello everyone, this is Puya. So let's continue talking about recursion. So one of the famous applications of recursion is solving the Hanoi Tower problem. I already prepared a video for you that explains how this can be solved recursively and non-recursively. So if you think about Hanoi Tower, where we have 3 rods or 3 poles and then n disks, we can solve this problem by first solving the same problem but for the first n minus 1 disks. So just if we can find a way to move the first n minus 1 disks to the auxiliary pole, then we can just move the last disk to the destination pole, and then again we can move the first n minus 1 disks to the destination one. So this is how the Hanoi Tower problem can be solved recursively. This is explained in detail in the video that I prepared. So you can watch that video if you want to learn more about Hanoi Tower problem. So this can be done. I'm just gonna skip this one. This can be done in 3 different steps. Move the first n minus 1 disk from source to the auxiliary pole or peg or rod, and then move the last disk from source to destination, and move the n minus 1 disk from auxiliary to destination. The base case, the stopping criteria, is once we only have 1 disk. If that's the only disk that we have, like, it's very simple, like we can just like move it from source to destination easily. This is the implementation of the recursive Hanoi Tower function in C++. So you can see that it's pretty simple. We have the number of disks, we have the from, which is the source and the destination poles, and this is the auxiliary or the buffer pole. If you only have 1 disk, then like we can just like move that disk from source to destination. Otherwise, if you have more than 1 disk, then like the problem is solved by first moving the first n minus 1 disks from source to the buffer or to the auxiliary pole, using the destination pole as the buffer, and then just move the last disk from source to destination. And finally, again, we're going to call the same function by moving the n minus 1 disk from buffer or the auxiliary rod to the destination rod, using the source as the buffer in this case. So you see that we have 2 recursive calls. We're calling the same function twice. Okay, and this shows the excuse me, this shows the running of this program for the case that we have 3 disks on poles A, B, and C. This is source, this is buffer, this is destination or auxiliary, and this shows like how the movements are going to be done to solve the problem. This is the recursive version of Hanoi Tower. I also provided the non-recursive version of the Hanoi Tower here, so you can see that I provided a class of a stack, a function to create stacks. We have 3 stacks in the main. You can see that we have source, auxiliary, and destination stacks, and we have a function for printing the moves. We have a function that decides from which, like based on the legal moves, which stack we need to push from, and how the disks are gonna move. And then another one that's another function that basically does the the moves, as I mentioned, that you saw in the video, that if I is the move index number, So if I mod 3 is equal to 1, the move it's going to be between source and destination, and we know if it's from source to destination from this function. So like we compare the top of source and destination stack, and whichever is smaller is the one that has to be moved from. And the same thing happens if I mod 3 is equal to 2, that the move it's going to be between source and auxiliary stacks. If I mod 3 is equal to 0, the move it's going to be between auxiliary and destination. Okay, I intentionally made a couple of mistakes or errors in this function, in this program. One of the mistakes I'll tell you, like here we allocate, but I'm not deallocating, so there is memory leak. I'm asking you to fix that. And there is another error that I want you to find out. This is going to be a good exercise to work with stacks. So I want you to analyze this code and find all the errors and fix it. Okay, basically it's a debugging exercise. So this is like again like showing like how the factorial function can be solved recursively. So like more about factorial function. This is a code analysis question again for you. So I want you to find out how this function works, and let's assume that if we pass number, let's say 4321, what does the function return to us, and what is this parameter with the default value is used for? Okay, so this is a good example for code analysis. Many of you asked me to see more practice question related to code analysis, so like try to find out like what this function is doing. Well, like the name is basically giving you a clue, but try to analyze it for the case where number is equal to 4321 or any other number. Doesn't matter how many digits it has. We talked about the stacks and call a stack and stack frame. So if we forget to provide a base case for the recursive function, we're going to have a stack overflow that crashes the program. And that's one of the disadvantages of recursion, because we're going to have a lot of memory spaces used, because we have like many function calls. So we have call a stack when we have a recursive call. I explained this in the class, and I'm gonna do it one more time. So we have two very basic searching algorithms. The first one is called sequential or linear search, where we start going through the array or vector or linked list one by one, like from beginning to the end or from end to the beginning. Like we start checking every single element until we find the target value. That's called sequential or linear search. It's in the order of n, because in the worst case scenario we're going to check all the n elements. And in this implementation we assume that we're going to return the first occurrence of the target value. We're going to return the index of the first occurrence of the target value in the array or vector, and if we can't find the target value in the array or vector, we're going to return number -1. You can implement this search algorithm recursively as well. So like here it shows how this can be done. We have an array, we have a target value that we are looking for, we have a start index and last index. So we want to search through this array from this index to this index, and we are gonna look for this value. So what we can do, we can just this is the base case. I'm gonna discuss this later, but If the array start index is equal to the value, then we are done. Otherwise, we're going to call the same function, right? Search through the same array, look for the same value, but we know that the first index or the start index didn't have the value, right? So we're going to increment the start index. We're not going to change the last index, right? And this is gonna basically call the function many times until either it finds the value or until the point that we get start index bigger than last index. So if the number doesn't exist in the array or the vector, we get to a point that the start index is going to become bigger than last index. So in that case, we return -1. So this is the base case for the situation that the number doesn't exist. Otherwise, we're going to return the index here at one point. Okay, so this shows the implementation of recursive linear search. We are searching through this array. We are looking for number x. We go from index L to index R, and this shows like how this can be done. Another searching algorithm that we have is binary search. The precondition for binary search is that our array should be sorted. Okay, so for applying binary search, we have to have a sorted array. And what we do in binary search, at each point we divide the array or the vector into two halves. We check the midpoint. If the midpoint is equal to the value that we are looking for, then we are done. If not, we check if the target value is smaller than the midpoint. If it's smaller, then it means that we only need to search through the first half. If it's bigger than the midpoint, we need to search through the second half, right? So with one question, with one if, we basically eliminate half of the search domain, okay? And this can be also be implemented recursively. So like in this case, we have a binary search function. We're going through this array. We are looking for this value. We search from this index to this index. I'm going to talk about this stopping criteria or base case a little bit later. But what's happening here, we find the midpoint by finding the average between a start index and last index. If the element at the midpoint is the target value we're looking for, we are done. We're going to return that index. If if the target value is smaller than midpoint, because our array is sorted, we are sure that we only need to search through the first half of the array. So we're going to call the same function, right? We're going to search through the same array, look for the same value, but from start index to mid -1, because we only need to go through the first half, which is going to go from start to mid -1. If that's not the case, it means that if array midpoint is smaller than value, it means that we have to look through the second half. So we're going to call the same function, look through the same array, search for the same target value, but this time with the start index equal to mid +1 and going all the way to the last index. So what we are doing, we're basically making a start index and end index closing to each other. We either move a start index close to last index or move last index close to start index, right? If the number exists in the array, we're gonna return an index eventually, like in this else block. If the number doesn't exist in the array, we get to a point that a start index is going to pass the end index, or end index goes before the start index. So if start index, this is going to go before the else block. If start index is bigger than last index, it means that the number doesn't exist in the array. So this is the base case or the stopping criteria for the case where the number doesn't exist in the array. So this is the recursive version of binary search. I'm showing the function here, again implemented in C++. Again, many novice programmers forget to put return here. We have to know that all the function calls of our binary search, they're supposed to return an integer, not just the last one, right? All of them have to have a return, right? In many compilers, even if you don't put return, it would still work, but like to write a complete program, you have to put a return here. This is again a very good excuse me, a very good code analysis question. This one, it's a little bit challenging. It takes like few minutes, at least half an hour, like at least like 15 minutes, like for like a novice programmer to analyze this code. But this function, it's a recursive function that would provide all the permutations of an array, of the elements of an array. So for example, if our array is ABC, this function would provide like ABC, ACB, BAC, BCA, CAB, CBA. Okay, and the way it works, I want you to analyze it, like for this example that's given. So you have to be very patient for this example because it has a lot of recursive calls, and it's gonna take a long time to analyze it, but it's a good example for code analysis. I also provided 2 links here so that you can see the visualization of Hanoi Tower and binary search recursive functions in the Python tutor website. I'm not going to go through it here, but you can check it out yourself. Some of the inherently non-recursive sorting methods like bubble sort, selection sort, and insertion sort, they can be also implemented recursively. I'm gonna go through it very briefly here. So I prepared a video that explains what bubble sort is. Like if you forgot what bubble sort is, you can check that video. But basically in the bubble sort, at each round we try to find the largest number and move it to the end of the array by swapping the adjacent elements if needed. Okay, so this recursive bubble sort, it has one loop, right, that just does that swapping. It finds the largest number and moves the largest number to the end of the array, and then it would call the same function, right, but for the first n-1 elements, because now we have the largest number at the correct location. So now we only need to sort the array for the first n-1 elements. This recursive bubble sort, it's not more efficient than the non-recursive version because it has many function calls. So bubble sort is not inherently recursive. Okay, you can implement it using nested loops. So like if we just like put this inside another loop with like n-1 iterations, this is going to be the non-recursive bubble sort. You can go through this example. Similar to bubble sort, we can also implement selection sort recursively. So what selection sort does, it basically tries to find the minimum number in each round of selection sort. We find the minimum number, and we only do one swapping, so that so like let's say like in this round, like we find 11 and we swap 11 and 64, and 11 would be at the right place. So I implemented selection sort recursively. So I wrote a function that's recursive itself, that like find the minimum index of and the index of the minimum number in an array from index I to index j. So this is like how this is implemented. So like we basically find the smallest number of the array from I plus 1 to j, and then compare that with AI. Okay, so whichever is smaller, that's the smallest index. So this is like how we have a recursive call, and like once we get to the point that we only have one element in the array, so like I and j are equal, then we return that index. So this is a recursive function that would return the index of the smallest number in an array. For selection sort, what we do, we find the smallest index, okay, and if there is a need, like if this is not at the right place, if this is not in the beginning, we swap it with the first element, and then we call the same recursive function for the same array for the same size, but we go from index plus 1 all the way to the end. So that's how the function works. And like you see that like index initially is 0, and we increment it in the recursive call. This like index has a default value equal to 0. I don't want to spend much time here because these recursive selections, these recursive bubble sort, selection sort, or insertion sort, they are not necessarily more time efficient than the non-recursive version. They're actually more like in terms of more time complexity, they take more time. They have the same big O notation, but they take more time because of the function overhead. They also like occupy more memory space because of the call stack. This is another recursive function that prints all the data values of a linked list using recursion. So like you remember that in order to do that, we have to traverse through a linked list, right? So we did that by saying that let's say p is equal to p arrow next, but here instead of doing it, we just we print the first data, and then we call the same function, but we pass the pointer of the original node. Okay, so we pass p arrow next, right? And once we get to the tail, once we get to the end of the linked list, once p becomes equal to null, then that's the base case we return. Okay, you can also like answer this question: what's gonna happen if we swap these two lines? Okay, that's gonna be a very good code analysis question for you. Like, what's gonna happen if we swap these two lines? Okay, once, like if we have the recursive call first and then we want to print. Okay, you can see that if we do that, we end up printing the linked list data from end to the beginning, from tail to the head, rather than like from head to the tail. Another sorting method that I explained in the video was insertion sort. So like in the insertion sort, we have a sorted portion and an unsorted portion, and we try to add elements from the unsorted portion to the sorted portion, and eventually the the whole array becomes sorted. Again, if you can't remember what insertion sort is, please watch the video. This one can also this is the non-recursive pseudocode for insertion sort. So you see that we have nested loops, right? We pick the first element of the array according to the I index, and then we go through the the rest of the array, and we compare the elements with the array I, and whatever it's needed to be done, we do, like we shift the elements to the right if they're needed. So like that's, for example, in this example, you see that here when we want to add 4, we shift 42 and 23 to the right and insert 4 in the beginning. When we want to add 16, we shift 42 and 23 to the right and we put 16 after 4. And the same thing here. So this shows the implementation, or sorry, the pseudocode for insertion sort. It's like time complexity, it's similar to bubble sort and selection sort. It's big O notation n squared. Insertion sort, this is the non-recursive implementation of insertion sort. You have nested loops. Okay. We basically search through the sorted portion, and we compare the elements with the elements that we want to add. If there is need for moving or shifting, we do that, and finally we insert the elements, that's like the first element from the unsorted portion, in the correct place, and this can go on many iterations. So this is the non-recursive version of the insertion sort. It can also be implemented recursively. It's not very time efficient. These are like just like for your practice, so that you get familiar with recursion. So first of all, if you only have one element, then we are done. Otherwise we say that, oh, let's just like first sort the first n-1 elements. Okay, if the first n-1 elements is sorted, right, then we just like need to compare the last element with the elements of the with the first n-1 elements and shift them if needed, and then insert the last node at the right place. So this is taking care of the recursive call, and just basically tries to make the array smaller and smaller until we only have one element, and we return, and then it would try to insert the elements at the right location. I prepared a video that explains this example very thoroughly. So this is how to reverse a linked list using recursion. So I explained 3 different methods for reversing a linked list. One of them is using recursion, the other 2 are non-recursive. One of them is using the stacks, the other one it's just like using pointers. So you can go through that video, and this example is explained there very thoroughly. You can also delete all the nodes of a linked list using recursion. So we basically say that, if you want to delete the list, right, if your head is like head pointer is pointing to the head of the list, we're calling the same function, would be passing head arrow next, right? This keeps going on until we get to the end of the array. Oh, sorry, end of the linked list. If that's the case, we return, right? And then it would start deleting the elements from the end, from the tail to the head. So one by one, everything gets deleted. I go through these examples very quickly because I want you to analyze them yourself. There's no point for me to do it for you, because you're gonna learn it once you do it yourself. So try to grab a piece of paper, write down a linked list, and try to analyze it. And then once you understand it, maybe you can also try to write the function yourself without looking at the code. I have another code analysis question. This is, we already did this. This is basically the Euclidean algorithm for finding GCD or highest common factor, greatest common divisor or highest common factor. This basically shows the Euclidean algorithm to find the GCD. I have two practice questions for you. So how to recursively reverse an array or vector. So how can you do that? So like the non-recursive version is basically if you have an array, you swap the first and last element, the second first and the second last, the third and the third last, and so on, right? So just write your function so that once you swap the first and last element, how can you call the same function with different parameters to reverse the rest of the array? Another one which is not that difficult, it's a very easy example. Given that you have an array, you're given an array or vector of integers, find the sum of array elements using recursion. So this is, again, it's not difficult, but like if you write this, you can understand the concept of going through arrays using recursion. Okay, so in the next 3 slides, I have some very important code analysis questions. So like the first one is using queues. So we have one recursive function here, function 1, another recursive function here, function 2, another recursive function here, function 3. Okay, try to analyze this code and understand what does each recursive function do. I don't want to give you any clue. I want you to analyze it. So maybe like create a queue and try to see like what this function do, what does this function do, and what does this function do. Try to go in order, function 1 first, then function 2, then function 3. The same thing for this one, but here we have a queue. Okay, so this function, it just basically it's a recursive function. It operates on a queue. The same, similar to this one. This one was Q2. Another function, this one, it's also a recursive function. We have stacks here, okay, and a third function which is also recursive. So try to analyze each of them and see what they do. And lastly, sorry, this is one example, this is another example. Okay, so this is like for queue, this is for stacks. And lastly, another recursive example with stacks. So this time we have a stack and a number x, and try to analyze this function and this function, try to see what they do. Like they are recursive, so you see that function 1 is called inside the function 1, and I want you to understand what these functions do. Like what does this one do, and then what does this one do. Pay attention here that function 2 here calls function 1 as well. So that's why I say like first try to understand what function 1 does and then do function 2. Okay, so that's all about recursion. I hope that makes sense. Thank you so much, and that's it for today.